Okay, welcome everybody. This is Physics 1051. Just assuming that everybody is in the right place. If you're in the wrong place, that's okay. You can get up and go. You don't have to sit through this if you're supposed to be in history or something. No, we're okay. I'm Kelly Shorlin, the instructor for the class. You can call me Dr. Shorlin, or I know it's a little old-fashioned. I also kind of like Miss. My pronouns are she and her. If anybody noticed the iPad here, this room is not equipped with lecture capture, but I am a big fan of the lecture capture system. So I've got my iPad pointed at the screen, and I'll record the lectures that way. I use the headphones, not as a fashion statement, but as a mic pack. So the iPad will pick up my voice. It won't pick up any of your faces. I don't think this is good enough to pick up your voices, so if you speak in class, I don't think it's going to show up on the recording. I'll post these to YouTube, and the link will go up on the course page. So if you have to be away from class, you will get some version of a recording anyway. I'd like to start our class with a land acknowledgement. I acknowledge that the land that we're meeting on today in this classroom is part of the traditional territories of the Beothuk and the Mi'kmaq. In this space, I'm going to do my best to share what I know and to learn from all of you and what you know. Physics knowledge, in particular, is kind of all around us, and it belongs to all of us, not to any one group of people. I'd like to acknowledge with respect the diverse histories and cultures of the Beothuk and Mi'kmaq, the Innu and the Inuit of this province. And as we go through our course, I would be very welcome to learn from any of you, any sort of alternate ways of learning and knowing as we go through the physics. So again, welcome to everybody. I'm glad to have you here. Physics 1051 is a pretty good course. It's going to take us more in depth about some topics you probably touched on in high school, but maybe didn't do lots of. We're going to start with a review of the syllabus. That's available in your Brightspace now. I have a handful of hard copies up here for people who like a paper copy of the syllabus. I'll do the highlights here, but you should certainly look through it because I can't mention everything. So for me, my office is in this building. It's kind of right above here, 358. My official office hours, this is when you're guaranteed to find me, are Monday and Wednesdays between 3 and 4. You're welcome to just drop by and come on in. Or by appointment. If these times don't work for you, you can send me an email and we can pick a time. In general, I'm in my office a lot. If the door is open, you are welcome to come in. If I'm working on something important, I've got the door closed and I won't answer it. If you want to contact me, email is the best way. Please don't use my Brightspace email. I don't remember to check it. So my preferred email is kshorlin@mon.ca. I do keep a Snapchat and a YouTube. Those are certainly optional, but they can be. Snapchat is not a bad way to communicate about physics problems. You can send me a picture of what you're doing. I can circle the place where you made a goof, and then we take care of it real quickly. YouTube is where I'll post the class lectures, and I've got some extra resources for Physics 1051 there as well. Our course information, everything is on Brightspace. I'm going to assume everybody is more or less familiar with Brightspace. If you're not and you need a refresher, let me know. We'll sit down and we'll go through it together. My primary way of communicating with you as a class outside of lectures will be through the announcements tools. So you'll get a little ding next to the bell and you'll see an announcement there on the front page. Everything is going to be there on Brightspace, including the link to your text. So the course textbook is University Physics, the 15th edition by Young and Friedman. If you go to the bookstore, I think they don't have any paper copies of the book. It's an e-text only. If you wish to buy that e-text, it's fine. You do not need the Master in Physics access code. We're going to do our assignments through Brightspace. If you wish to buy a second-hand copy of the textbook, that's absolutely fine. Some people might have paper copies left over from when they still gave out paper copies. If you wish to use a different textbook, that's fine too. The physics hasn't changed in over 100 years. It's all the same stuff. Just make sure you get a calculus-based textbook. You can borrow one from the library. You can use what we've got up in the Help Center while you're there. So kind of any first-year physics textbook should be fine. Survey is a popular author. That's kind of the go-to. You should be able to get a second-hand Survey almost anywhere. So if you don't want this book, you can use any of those. If you do get the e-textbook, the way to access it is to go to our Brightspace page. On that Brightspace page is a Mastering Physics widget. That is the only way you can access the course. So here's the Brightspace page. Here's the Mastering Physics widget. You click on this. This is where you get access to your e-textbook. If you go any other place, it's going to ask you for secret codes, which you don't know, but this will take you right there. Let's see. These are the topics we're going to cover in this course. We should get through all of it. Sometimes, depending on how fast we go, we don't get to wave optics. That's why I've called that one optional. You should be working with your textbook along with the lectures for extra examples, a deeper understanding. So you should be reading your book as you go. I certainly recommend everybody has a textbook. For the distribution of grades, people seem to care about this one a lot. The labs are worth 15% of the course. There's a separate Brightspace page for the labs. If that's not open yet, it will be soon. Labs start next week. Our lab room is just around the corner, 2039. We have 6 labs. Dr. Ming Lee is our lab instructor, and he would be your go-to contact for lab concerns. Unless, of course, it's something you prefer to keep private between me and you, and then, of course, I can deal with things as well. I figure everybody has got the science safety courses done, but just in case you don't, you do need to do those. You do need to pass the labs in order to pass the course. So a person who's scoring A's on their term test assignments and final exam, but blows off 4 labs, will in fact fail the course. So you're expected to show up for all 6 labs, and you need to pass the labs to pass the course. If you are repeating the class to improve your grade, you do also have to repeat the labs. There are no lab waivers. We also have problem sessions. Those are like study periods. They alternate with your labs. They're in the lab room. We'll work on problems. You'll get lots of support for the first hour. At the end of the first hour, you do a small quiz. The quiz isn't intended to be really difficult. It's more of a check-in. Do you understand the basics? Do you know the definitions? Can you put the numbers into an equation? But it is intended to help you start to get ready for the tests. Our assignments are worth 10%. Those are all found on Brightspace. You click assessments, you click quizzes, then there'll be assignment 1, assignment 2, and so on. I think I have assignment 1 open now. If I don't have it open now, I'll get it open by tonight. With these assignments, the goal of them is not to be a hoop you have to jump through to get through this course. That is not the point. I'm not trying to get you to do useless tasks to waste your time. The goal of the assignments is to help you master the material. Some of them you really have to think about and puzzle over. You can cheat on them. Lots of ways to cheat out there. But if you cheat on them, then you're probably not going to do very well when that question shows up on a test. So that's the point of the assignments. To that end, you have unlimited tries on the assignment. So you can try 1 billion times if you want to, as long as you just get it all submitted by the deadline. So that's the goal there. If you find you need help on the assignments, and you may well, some of them are designed to really challenge you to think hard. That's what's going to lead you to success. If you need help, I suggest you work with each other. Some classes like to set up, I can never remember what this is called, Discord, is that a thing? Some classes like to set up a Discord. So if one person wants to set up a Discord, I guess you would email an invitation to the rest of the class. That's not something I'm part of. But that's a good way for you all to communicate with each other. You can work in study groups in the help center or whatever, but I do encourage you to work together. It's a great learning tool. The Physics Help Center, I haven't seen the schedule yet, but I think it's open 10 to 3, Monday to Friday. Staffed full-time, you can get free help. It's just a drop-in service. You drop in and you say, look, I'm having trouble with this. Here's what I've tried, and they'll guide you to get you a little bit further. So the Help Center is a great resource. We're going to have 2 tests in this class, October 13th and November 17th. They're going to be in the class period. The room is a little bit cramped, so I might try and find a different place for us to write it, but those will be the times for it. The final exam is worth 40% and will cover things from the entire semester. Okay, any questions here? To go along with sort of the not cheating on the assignment, academic integrity is really important. That means that you don't copy from each other. Like for example, if you're in the lab and you're working on something, you wouldn't look at your partner's question 7 and copy it word from word in your book. You're all welcome and encouraged to share ideas and concepts, but when it comes time to put pen to paper, you're putting your own thoughts and ideas down in your own words. You're also not allowed to take any of the class materials and upload it to any website online. I know a lot of these pay-per-use websites are super popular where you get to pay for your assignment answers. That's kind of a double whammy. It's theft of intellectual property, which has legal penalties, and it's academic misconduct, which has academic penalties. So nothing from the class is allowed to go up online. If you're ill, and certainly that happens, you know, in general, you're expected to show up for all your evaluations. You can't just blow them off because you don't want to do it. But if you're out ill, that can happen. What you have to do is if you miss something, you have to get in touch with me from your MUN email within 48 hours. If I hear from you within the right time frame, then I can provide you with some accommodation that we'll decide as we go, whatever is the most suitable. If you're out for more than 5 days, I might ask for a doctor's note to go along with that email. So if it's just a cold for a few days, the email's fine. If it's a long-term illness, you're in the hospital for 3 weeks, I might ask for a note. Resources. CITL actually has a lot of good stuff, so I've got their information up there. These are the 5 main people you'll get to know in the Physics Help Center, along with a bunch of the faculty. So you can drop in there anytime, you can ask anything you want, not just about assignments, like if you're struggling with the course ideas, they can help with that as well. So Help Center is a great resource. Physics 1051, I think it gets kind of a bad rap. People say it's really hard. I don't think it so much is, especially because I've tinkered with it over the past few years to make it kind of really targeted for first year success. And I believe that everybody sitting in this room can be really successful in this course as long as you do the work. So everybody in here is walking in with a chance to walk out with an A. I believe it with my whole heart. To do the work, I think it's pretty important to come to class. I will have the lectures up on YouTube, but maybe it's hard to learn from watching lectures on YouTube, so I recommend you come to class. I recommend that you take notes. There's some well-documented evidence that writing notes, particularly with a pen or pencil, it helps your brain absorb and assimilate and retain the information. So I will be making notes as we go. I recommend that you make notes. As an accessibility issue, some people really struggle when they have to sit next to a screen. So I'm just going to ask that the first 2 rows of the class after today, the first 2 rows don't have any screens. So if you want to make notes on your iPad and your laptop, I'll just ask you not to sit in the first 2 rows, please. And then if anybody has trouble sitting next to a screen, they can sit in the first 2 rows and they don't have to kind of deal with that. So I'll ask for that, please. Almost every class, I'm going to give you some homework problems. This is not stuff you have to pass in and get graded. This is extras for you to practice on, and it's often where I draw test material from. So I'm going to recommend that you work on the homework as well on a regular basis. I'll always post the answers and the solutions for you to check in. I'll also post the lectures. As I make notes, I'll keep those slides and I'll post them after class. So if you miss things during class, you can always go back and get it. You should probably be prepared to study. Like the rule of thumb is for every hour in lectures, you spend 3 hours outside of class. So you're probably look at all of your studying taking about 9 hours a week. You know, that's kind of a target. Some people it's going to be less, some people it's going to be more. Some topics will be less, some people will be more, sometimes it'll be more. But that's kind of a rule of thumb. It's really important, maybe especially in physics, to struggle, to look at a problem, to maybe not really understand it, to try and figure it out, to try and get an answer, and to get that answer wrong. That's a really big step in learning. Then you go back to the problem and you try a little more and you text your friend and you try something else. Maybe you get it wrong. Then you go to the book and you try a little more and this time you get it right. That's kind of the path to success. It's that struggle that helps you learn to figure out how to figure these things out. And it's not always that easy, but the process of being wrong is really valuable. I really wish I had $1 for every time I was wrong in my life. I'd be off on a desert island somewhere. I think one thing that can help you stay on track, and I like to do this with all my classes, I think studying a little bit every day is a good idea. And I put my money where my mouth is. I'm trying to learn French. I'm at over 5 years doing some every single day. And I'm getting better. I'm definitely learning. I got complimented when I went to St. Pierre. If you all can keep a physics streak, which means you do some physics every day between today and the last day of classes, so you study some physics, then I will give you a prize when the semester is over. Okay? I think that's not a bad deal. Any questions? I usually get 2 questions here. Yep.
Yeah, how would you keep record? How would you know?
How do I keep track? That's normally the first question. The answer is, I'm going to believe you won't lie to me. If you send me a message at the end of the semester and say I did it every day, I choose to believe you. I choose to believe nobody's going to tell me a lie. Okay, anybody got question number 2? Question number 2 is often, what's the prize? The answer is there's only one way to find out. Okay, you keep the streak, you'll find out about the prize. I'm happy to say that every semester I do give away prizes. During COVID, when we had to learn from home, I must have mailed out 2 dozen of them. I think people didn't have enough to do. So there are prizes for the getting if you stay on top of your physics. Okay, then last, I guess not everybody is first year, maybe some people, but I think this is still important even after your first year. Like, you're all human beings, and student is just one facet of who you are. You have families, relationships, jobs, volunteer, commitments, hobbies. So you might well come to a place this semester where you're finding things difficult. It happens. If you come to a place where you're struggling, there's a lot of help out there. A lot of it's on campus, some in person, some online. Student Wellness has a lot of resources. If you find you're having a rough go of it and you don't know what to do, come talk to me. I probably can't solve your problems, but chances are real good I can set you up with somebody who can help. So if you're having a tough time, please kind of come talk to me, because I definitely want you to succeed. Okay, that's most of the course stuff. Any questions so far? Super. Oh, one thing I forgot to mention, I mentioned about how you can't kind of post any of these things online. You also can't do any recordings in class, so you're not allowed to record the lectures. I do it for you. So if people have their cell phones out, I'm not going to be the cell phone police. If you check the text in class, I'm not going to say anything about it. But if you hold your phone up like this, I will ask you to put it down, because I can't tell if you're taking pictures of the screens or if you're checking Facebook. So just if you hold it up, I am going to ask you to put it down. So next, I just want to do a little segue into starting our course. Physics, I think it's super interesting. It's kind of a study of the world around us, you know, and we're learning about the things that we interact with. And the overall learning objective that I have for you for this course, what I want you to take away from this course, oh, that was weird, is I'd like for you to be able to look at a problem or a situation and think critically about it. What do I know? What does this mean? What is it telling me? What do I not know? I'd like you to take that bit of information that you've thought about. I'd like you to think about the things you've learned in this class. Ask which of those things are applicable, which are not applicable. And I'd like you to be able to put those 2 things together and find a solution to the problem. Overall, people who do physics degrees, that's kind of the outcome. Physicists are problem solvers. Doesn't matter what the problem is. Physicists see something and say, oh, I'm going to fix that. It's just kind of how we work. And that's my goal for you, is to be able to kind of meet that objective. That said, I think it's really important for you to have your own goals. So before we quit for today, I'm going to ask you to do an exit slip. I'll just give you a heads up in case you want to think about it before you have to do it. And on the exit slip, I'm going to ask you to tell me, what are your goals for this class? What do you want to take away from this? and what are a couple of concrete steps you're going to do to meet your goal. So we'll get to that at the end of the class. We'll quit a few minutes early so that we can do that. Okay, so that's everything about the course. Questions? No, we're good. So now we're going to jump into our material. The first thing we're going to do, last semester was really kind of funny, last winter. So lots of you, some of you, did Physics 1050 last winter. Some people might have been last fall. And we had this strike right in the middle. So 1050 might have been a funny beast for you last winter. You're supposed to come into this course knowing about simple harmonic motion. That's chapter 14 in your textbook. I'm going to do a quick review of simple harmonic motion so that you get all the terminology, kind of the general basics. If that's, excuse me. I'm really sorry. I had a cold over the weekend, and I still kind of have a dry throat. I'm trying really hard not to cough. So I'll take you through the basics of chapter 14 because we need those concepts to start with chapter 15, our traveling waves. If the review I do, it'll take us to the end of today, maybe a little bit into Friday's class. If this is not enough for you, that's fine, I understand, especially if you got your 1050 messed up last winter. I do have a longer review posted on Brightspace. There's at least one video that goes through all the material at a careful pace with a bunch of examples and some stuff to work out. So if this is not the coverage you need, just check out the stuff on Brightspace. I picked this picture to put up on the slide when we're talking about simple harmonic motion, because it turns out when dogs pant, I guess most people know that dogs pant, they actually pant at a particular frequency, and it's the frequency that's harmonic with their own respiratory system that lets them cool the most efficiently. So I think that's kind of a really neat little application of simple harmonic motion and resonance. Okay, so now we'll get into our review. So for simple harmonic motion, the one we look at mostly is a mass on a spring. Okay, there's lots of other simple harmonic motion, but this is the easy one. So I've got a couple of springs. I figure everybody can see them. I got a red one and a blue one. They have different stiffnesses, different spring constants. So when I put different masses on them, they'll stretch by different amounts. So the springs are on the stand now. They're not moving, or not moving very much. That means they're at equilibrium. When I put a mass on it, the weight is going to pull down on the spring, and it's going to come to a new equilibrium. Okay, they're different masses, different spring constants, so they stretch different amounts. So they come here and they hang at this point, and they're at a new equilibrium because they've stretched down a distance, and we'll call that distance y. So here's our spring at its equilibrium length initially. We put the mass on, and it stretches down some distance that we call y. So the amount of stretch we would call y. Typically, that's going to be measured in meters or centimeters. You know, you can do millimeters and microns and stuff, but meters and centimeters is what we'll use the most often. When the mass comes to rest at its new relaxed position, that's the new equilibrium. So this line represents the equilibrium. And we call the equilibrium y equals 0. You don't have to call it y equals 0, but it makes life easier. So our equilibrium is y equals 0. At equilibrium, it's not moving, so the acceleration is 0. Okay, so it's not moving up and down. If the acceleration is 0, it means that the net force is 0. So when we've got it hanging right here, it's at rest. That's what equilibrium means. It means that the net force in the y direction is the mass times the acceleration in the y direction. To figure out those forces, we draw a free body diagram. The Earth pulls it down. That's the force due to gravity. I have to make that force kind of small because I didn't leave myself much room. and the spring pulls it up, that's the spring force. So that's why it's at rest, is because the spring force is going to be equal to the size of the gravitational force. So Fs here is what I wrote for my spring force. It's a vector. It's given by Hooke's law. You hopefully remember that from your physics 1050 or 1020 or 1021. It has units of newtons because it's a force. A spring force will always pull something towards equilibrium. So that's why it's called a restoring force. So you probably learned about restoring forces as well. Okay, what next? So the sum of the forces in the y direction is mass times acceleration. We've got the spring force that points up. Our spring force is given by k times the distance to equilibrium. K stands for our spring constant. It represents how stiff the spring is. That has units of newtons per meter. So spring constant times distance from equilibrium points up, so it's positive. And then we have gravity pulls down, so that's mg. Negative because it points down. Our acceleration is 0. So ky minus mg equals 0. If this were a problem we were studying, I might start off this by saying I put a 500 mass on a spring. It stretches down 10 centimeters, find the spring constant. You know, that would be a typical part A of a problem. And then you would get it oscillating and figure out other things. So that's something you can certainly do. So that's at equilibrium. Then what we do next is we push our mass a little bit. So I'll let it go up a little bit. And then I let it go. And you see it starts to oscillate. So this goes from up to down and back up. When it goes from up to down and back up, that's one full oscillation. And when we analyze the motion, it's important to know about how long it takes for one oscillation, that's the period, or how many times it oscillates per second, that's the frequency. So we care about the period, time for one oscillation, so it goes from this point down, back up. That's one full oscillation. So the period is how long that takes. That usually has units of seconds. And frequency is the number of oscillations per second. That's 1 divided by the period. That has units of seconds to the -1, or hertz, which is hz. And then amplitude is our maximum distance from equilibrium. That's represented by an A. So that's how much I pushed it up by. So it goes up by a distance A from equilibrium, and it can go down a distance A from equilibrium. So one oscillation is from where it starts back to where it started. Still good? So I'm anticipating that this is a review for most people. If you did physics 1021, you probably did a lot of this in 1021. It's like extra review if you did it in 1021. Okay, so there's some of the basics. So we said to think about the motion, we need period and frequency. That's certainly true. When we want to analyze the position, we want to say where the mass is as a function of time. So how does it move over time? I'm just trying to let people get caught up on the notes before I move on to the next page. Okay. So for our description of the motion, we want the position as a function of time. So we're just going to change our geometry a little bit. Instead of having a vertical mass on a spring, we're going to have a horizontal mass on a spring. So we're going to say we start with a mass like this. We're going to pull it out some distance that's equal to the amplitude. We're going to let it go, and it's going to oscillate back and forth this way. Because this is a horizontal motion, we're going to write an equation for x as position. So we start with our mass right at the center. That's the equilibrium position, x equals 0. We're going to pull it out some distance. That distance is going to be the amplitude. So we're going to pull it out to here. Here's where we're going to release it. When we release it, it's just starting to move. So at the release point, the velocity is 0. It's not moving yet. So at the amplitude, where x equals a, your speed is equal to 0. We release it, it's going to move towards the equilibrium because the spring force pulls it towards equilibrium. It's going to keep going because it's moving fast here. The spring force is back towards equilibrium, so it's going to slow down until it gets to x equals minus a. When it hits x equals minus a, that's where it's going to stop and turn around and go back. You probably called this a turning point in physics 1050 or 1020. It's going to go back, and it will get back to the amplitude again, and there's one full cycle. So that's one full oscillation. When our mass is off to the side like this, we could draw the spring force on it. So here's where it is. We've got it out at equilibrium, or we've got it out at the amplitude, and we've just let it go. It's got a spring force on it that's pulling it to the left. If we write our Newton's second law, we will say that the sum of the forces in the x direction equals mass times acceleration in the x direction. So let's use that to figure out our equation for position. Our spring force is given by kx. It points to the left, so it's going to be negative. So minus kx equals mass times acceleration. This is an equation we'd like to solve. People who've done a differentials equation course probably learned how to solve it in that class. So here, we're going to remember that acceleration is the derivative of velocity with respect to time. But velocity is the derivative of position with respect to time. You see here we've got two d by dt's. That makes acceleration the second derivative of position with respect to time. Second derivative just means you do the derivative twice. So you take the derivative of x once, you get velocity. You take the derivative of that, you get acceleration. That's what it means, that acceleration is the second derivative. I'll put this in right here for my a. Minus kx equals mass times the second derivative of position with respect to time. We can rearrange this equation a little bit just by dividing both sides by m. So we get that our acceleration, or our second derivative of position, is minus k divided by m times our position x. People who have done a differentials equations class, this should be a really familiar form. You don't have to know how to solve this equation for this class, okay? So that wouldn't be something I would ask you to prove what the solution is. But it is a form I expect you to recognize. So if you saw an equation like this, you should be able to recognize that the solution is a sinusoid. So the solution is that the position as a function of time is equal to some maximum position, that's the amplitude A, times cosine of omega times t. Omega is a number, a value, given by the square root of k over n. One of your homework questions is, I'm going to ask you to take this solution and show that it works, show that it fits. So that's one of your homework questions for today. So let's think about what all this means, what we're going to do about this. We talked about the speed was 0 at the amplitude and the negative amplitude. That's where it turns around. Those are the turning points. If our speed is 0 out at the two ends, then our velocity is a maximum in the middle. At the equilibrium, velocity is a maximum. And that makes sense because as it approaches equilibrium, the spring force speeds it up, it's getting faster. As it moves away from equilibrium, the spring force slows it down, it's getting slower. So it's at its maximum speed right there at equilibrium. So when x is at the amplitude, the speed is 0. When x is equal to 0, the speed is a maximum. We could draw a graph of the position as a function of time. So position goes back and forth between plus and minus a. And it goes as a cosine, looks like this. My drawing skills are not the best, but hopefully that's not too bad. So where x is an amplitude or a negative amplitude, we know that v is the slope. Well, v is the slope anywhere. V is the slope at the amplitude and negative amplitude. It's flat, that's where our v is equal to 0. At the equilibrium, that's where our slope is a maximum. That's where our speed is a maximum. Okay, any questions here? Okay, and we'll see forms of these graphs coming back when we start to talk about traveling waves. So this shape will come back. All of these slides I'm going through here, I do post them on Brightspace before class starts. These slides are up. I think some people already printed them off. I've got the next chapter already up, and I don't think I've got chapter 16 up yet, but we'll spend some time on 15. So I would recommend that before you come to class, you kind of print them off or make a sketch format in your notebook or download them to your iPad so that you can make the notes as we go. So I'll always make those available before class. If you have those slides, you'll notice that the next slide is a couple of homework questions. I will post the answers for those so that you can check and see how you're doing with it. Okay, so that's our general form for position. Any questions before we move on to the next thing? So this slide has just got a couple of nicer set of notes for you that you can have on hand. What we'd like to do next was, we said that x was a times cosine omega t, where omega is the square root of k over m. That's definitely true. This is for a mass on a spring. We'd like to do just a little bit more work with this omega to see if we can figure out what this means. So from whenever you studied circular motion, things going around in an orbit, you probably learned about angular frequency or angular velocity omega, where omega was 2 pi over t. We're going to bring that in here to this class. So there's our general form. On our graph, the period is the time it takes for one oscillation. So that would be from the amplitude back to the amplitude again. That's one period. And to go back to the amplitude again would be another period. So our cosine graph repeats every period, right? That's how cosine works. It repeats periodically. It's a periodic function. Because it repeats every period, a way we can write any sinusoid, x of t, would be the maximum value a times cosine 2 pi over t times time t. So this little t is our time. And the big T is our period. Okay, so cosine 2 pi over period times the time gives us a graph that repeats every period. That's how a cosine function works. So this is any sinusoid in general. This is for a mass on a spring in particular. So if we have a mass on a spring, omega is root k over m. We also know that omega is 2 pi over t. That's a definition we have from when we talk about circular motion. So what we know is that omega is root k over m for a mass on a spring, and is also equal to 2 pi over the period. And if you remember that 1 over period is frequency, you could also write it as 2 pi f. This is your angular frequency. And once in a while, I might also call that angular velocity. It means the same thing. So your frequency tells us the number of oscillations per cycle. Angular frequency omega is similar, but it gives you the number of radians per second. So instead of cycles per second, it's radians per second. So the units for omega are either radians per second, the radians comes from your 2 pi, or seconds to the -1. Those are both acceptable units for omega. Radian is not a real unit any more than an oscillation is a unit. That's why you can say seconds to the -1. And this brings us to a pretty good tip. When you're doing stuff about waves and simple harmonic motion, your calculator needs to be in radians mode. If you've got it in degrees mode, your answers are not going to come out right. So radians motion when you're doing all, radians mode when you're doing all this stuff. Okay, questions? All right. So that's position as a function of time. Let's also get velocity and acceleration. So here's our graph of x versus t, so position as a function of time. I've labeled period in 3 different places. To go from amplitude to amplitude, equilibrium to equilibrium, or negative amplitude to negative amplitude. It just shows that one cycle is from one spot back to the exact same spot. Any of those is a valid place to call your period. Our position graph goes between positive and negative the amplitude. So the amplitude is the maximum value. Typical units are meters or centimeters. And t is our time for one oscillation. We'd also like to think about the velocity as a function of time. So we can think about our graph right off the bat, where x is equal to the amplitude, our v is equal to 0. Where x is equal to 0, our v is a maximum or a minimum. Let's get the equation for that. We know that velocity is the derivative of position. I'm going to say follow steps. To get into this class, you had to have done Math 1000, so I'm assuming you're comfortable with derivatives. I'll post the steps for anybody who wants a refresher, and I will just give you that the equation is minus a times omega times sine omega t. So that's the equation for velocity as a function of time in simple harmonic motion. You get that by doing the derivative. What we notice is that we've got the same omega here and here. That means we have the same period. So position and velocity have the same period. So from here to here is still our period t. X is measured in meters, but v is in meters per second. So they can't have the same maximum. They have different units, they have different maximums. So if you were going to ask what's the maximum value, you could figure that out by thinking about sine a little bit. So sine in general can oscillate between 2 values. Can anybody tell me what's the maximum and minimum that sine can have? I think I heard it, but not very loud. 1 and -1 is exactly right. So when you do sine on your calculator, the biggest you're going to get is 1. The smallest you're going to get is -1. Let's think about those 2 extreme values. If sine omega t equals 1, then v is equal to minus a omega times 1. V equals minus a omega. Some people would call this the maximum velocity. I wouldn't because it's negative. That's a valid argument to make, so you can go back and forth on whether or not negative is okay. I say it's not. If sine omega t was equal to -1, then v is equal to minus a omega times -1. V is equal to plus a omega. For my money, a positive value is the maximum velocity. So the maximum your velocity can be is the amplitude times the angular frequency. So that's your Vmax. That's negative Vmax. And this would be measured in meters per second or centimeters per second typically. Okay, any questions here? Oh, it's still good. Okay, we still have 5 minutes left, but I want to give you enough time to think about those exit slips. So I'm going to stop with this for right now. We can finish this up when we're back on Friday. So for your exit slip, I'm going to ask you to take out a piece of paper and write your name and student number. If you don't have any paper with you, can you kind of look around hopefully? If you have paper you're willing to share, can you look around with a welcoming smile and pass some out, please? And I have some paper up front if anybody wants to come up and grab a sheet. I will ask you to please put your name and student number. And I'm going to ask you to pass this in at the end of class, which is why I'm asking you to write it on paper. Oh, I didn't bring extra pens, so I'm sorry. I'm thought about pens. If anybody has a pencil they can share, I'll check my... Okay, I've got like 4 pens here. Get a pen. Okay, and then there's paper here. So, name and student number, please. Question 1, what is your specific goal for this class? And then what's a couple of steps you're going to take? Did you want paper and pen? So what are you going to do? And then if you want to keep it as a motivational thing for yourself, maybe just snap a picture of it before you go. And then just leave that up at front for me, please, and then you're good to go.